Hello and welcome back. In the last lesson, you learned to train a neural network to classify between handwritten digits. Now we move on to testing our model by grabbing an image from the web. The image you can grab from the previous article, and once you grab the image URL, if you were to paste it onto Google, like so, make sure to remove the string quotes. You shouldn't have them in yours, but I had them in mine. In doing so, you'll realize it's the number 5, which is what we'll try to get our network to predict. And so using this link, we can perform a GET request to retrieve the image data in our notebook. To make a GET request, we will need to import requests right onto the cell. So we import requests. And now we set a variable equal to the URL that we just talked about. And now what we do is we set a variable response is equal to request.get, and that's going to take in the URL where we'll be obtaining the image. And what we'll do is set stream is equal to true, so that the request doesn't first download the entire image into memory. And if we print response and run this code until it gets executed, name requests is not defined. Let's try that again. We get a response of 200, which indicates a successful GET request. We can now use the raw content of our response to obtain the image. But first, what we got to do is from PIL, from the Python imaging library, we must import the image module. And now what we can do is set image img is equal to the image module dot open, and we'll use that to identify the raw contents of our response, response.raw. And now we can plot the image to make sure everything worked out with plt.imshow, and the first argument is the image itself, and that is all. Getting rid of this print statement and running the cell. We get an error, module pil.image has no attribute register extensions. In the case of such an error, we must install the Pillow version 4. If you do get this error, I recommend following along with this. If you don't, then feel free to proceed with your current code. In my case, I will go on this top cell and press Alt-Enter to create a new one. And over here, I will pip3 install Pillow is equal to version 4. Like so, waiting for this to complete. All right, and rerunning the following cells, we get our image. Now before feeding this image into our model, it must be pre-processed. We need to ensure that the image corresponds to what the neural network was trained to learn. This is what the image should look like. We should make it into a 28 by 28 grayscale image like the ones in the training data. Our image is plotted to be 1000 by 1000. The first problem one can easily identify, however, is that our neural network was trained on images with a black background and a white foreground. In this case, the image has a white background and a black foreground. So the first step in pre-processing this image would be to, on this bottom cell, set image is equal to the Python imaging library dot image operations dot invert, and we will invert our image, which would simply invert the colors of our image, I should say. Ultimately, our image will end up having a black background with a white foreground as intended. And currently this image that I picked out for you, it's an RGB format with 3 channels of pixel intensity values. This is problematic for numerous reasons. We must convert this image to be a binary black and white image. And we can convert this image with img is equal to img.convert. And by putting 1 as an argument, it converts it to the intended bi-level image. One more thing we must do is transform this image the same way we transformed all of our other training images. So we set image as an argument of the transform variable that we initialized earlier. Transform. And recall, we said this image was way too big. We need to ensure that it's 28 by 28. So in our transform chain composition that we specified somewhere over here, it's right here, what we're going to do is add an extra transformation. Transforms dot resize, and I want it to be 28 by 28. Rather, I want every image that gets transformed by the set of transforms to be resized to be 28 by 28. This will simply act to resize our new image, and given that these transforms are also applied on the training and validation data sets, this transform right over here should not have an effect on our MNIST images, as our MNIST images are already 28 by 28. All right, finally, we plot this image. Well, before doing so, let us store the result onto a new variable, img. And finally, we plot this image with plt.imshow. And since the image is now a tensor, since we pass it to the transform chain composition, remember one of the transforms is 2tensor. And since the image is now a tensor, what we must do is convert it to a NumPy array with image convert, the function that we specified earlier, img. All right. And the reason for this error is because on the cell below this one, what we're going to do is import pil.imageOps, like so. Trying this again. And perfect. It looks very similar to our MNIST images. Now, our pre-processing technique was indeed successful. It's a 28 by 28, black background, white foreground. We can now feed it into our neural model to make predictions. We do this the same way as we did for MNIST. So for now, I'm just going to go back up top here and copy the following. The following code, which we use to make predictions, right over here. We can delete the loss and modify these variables accordingly. We set image is equal to image.view, image.shape. This will be image itself, since we're just passing in the image onto our model. In this case, we're just going to call this output, since we are receiving only a single output and a single prediction from that output. All we're doing is reshaping the image to be 1 by 784, as that is what can be fed into the model. And upon feeding it into the model, it will result in an output of scores. We take the class with the highest score and store it onto pred. And now what we can do is, through the variable pred, print pred.item. And it makes the accurate prediction. This is really good. We grabbed a random image from the web and our model classified it correctly. Let's do one more test before calling this lesson off. Back to this cell on top. Although I should be using functional programming, just to make this process faster, we're going to copy and reuse the following right onto the last cell. We are reusing the code for displaying a grid of images. And now this batch of images that we get, I want to pass all of them into our neural network so that we can visualize the evaluation results to make predictions on these images. And rather than grabbing images from the training loader, we will grab them from the validation loader. And to make predictions on these images, once again, we reshape them in much the same way. Right below data_iter.next, we set the following, except this will be labeled as images is equal to images.view, passing in the appropriate images.shape. This is just going to be 1. Again, we require the output of all the images and the prediction as well. Calling this preds is equal to torch.max output. So to make predictions on these images, once again, we reshape them in much the same way and changing the variables accordingly. And having performed predictions on all of these images, what we want to do is modify the title of every image that's being iterated through. So we put axis.setTitle and first placeholder and a second one. .format. The first placeholder will contain the prediction of the images that's currently being iterated through. Preds index.item, idx.item. And alongside the prediction, we put the label of the image that's currently being iterated through. Labels, idx.item. And we are actually going to make both of these into strings, str, as well as this one, stringify it, str. And what we'll do afterwards is actually set a color. Color is equal to green if the prediction preds at index is actually equal to the label labels at index. If the prediction of the image currently being iterated through does not match the label of that image, else we set the color equal to red. We're missing a bracket here, and we should be good to go. All right, it predicts all of them correctly, except one, which it gets wrong. And that is to be expected from our deep neural network. Because realistically, image classification is best done with a convolutional neural network. The accuracy for a deep neural network for such a purpose would pretty much just plateau at a certain point, and any attempt to improve it by adding more hidden layers or more nodes would likely result in overfitting. There are other reasons why we tend to not use deep neural networks for image classification, and one that really stands out is currently we're dealing with grayscale images, which are indeed computationally manageable by the feed-forward neural network. They are simply 28 by 28 with a single channel of pixel intensities, which means 784 pixel intensities in the input layer. And since each node in the hidden layer is connected to every single node in the input layer, each node in the hidden layer would then be parameterized by 784 weight parameters. What if one was dealing with an RGB image that's 72 pixels wide, 72 pixels high, which corresponds to 5,584 pixel intensity values? And since we're dealing with a 3-channel colored image, multiplying that by the number of channels results in 15,552 weight parameters for each node in the hidden layer. And as such, we just wouldn't have enough computational power to train the sheer size of the neural network. This is why we use convolutional neural networks, which also makes processing a lot more computationally manageable. We will discuss convolutional neural networks in the next section.